Both questions will involve guess cubs and solve. So it's basically going to be two questions. One of them is going to be I equals Q over T. One of them is going to be V equals E over Q. Involve guess cubs and solve. You will get possible enriched credit for not using the purple sheet, for having no scaffolding, for having correct sig figs, and there will be another one for unit cancellation. Okay, so that's going to be like where you have T is equal to Q over I, which is equal to coulombs over coulombs per second, which is equal to coulombs times seconds per coulomb equals seconds. Or it could be Q is equal to I times T, which is equal to coulombs per second times seconds, which would equal coulombs. And the same sort of a deal for voltage. Do you want me to write down the voltage ones? Okay. Voltage ones. We have E is equal to VQ, and so then if we have our voltage is joules per coulomb times coulombs, that's going to give us joules. If we have Q is equal to E over V. Energy is measured in joules. Volts are joules per coulomb. So that's going to be joules times coulombs per joule equals coulombs. Does anyone want a printout of that? Okay, I will do that right now. Print screen. There we go. Doodle-doo-doo. Who doesn't want one of these? Okay, I'll make one for everyone. So that's about 25. So I want 13? 13. Okay. We are now going to be on page 82, which is 6.3c. So you're looking for this little guy in the cowboy hat. And if you're having trouble finding it, let me know so I can help you out. Ryan, do you have your book today? And we're going to start by watching a little video. Now, I have a little pod I have a little 5 people over here who aren't very good at watching the video. They're much better at watching each other. That might improve future robots. Okay. So, if you like sitting where you're sitting for the rest of the week, please pay attention. And if you don't like sitting where you're sitting, I can easily make arrangements because a whole bunch of people are taking off my vacation early. Aren't they lucky? And I can make permanent arrangements for the rest of the week. Okay, so pay good attention during the video. Okay. Here we go. We are going to learn today about electrical resistance. Oh, I need my plug-in of sound. You don't need to write anything. We're just going to watch. And once we have watched, then we'll go over it together. I'm going to put on subtitles because he's got quite the accent. Okay, let's start that over again. Okay, so resistivity is something that each material has. Copper does not have a high resistivity. It has a low resistivity, which is why we use it for conducting electricity. Things that conduct well have low resistivity. Things that conduct poorly have high resistivity. The length, it matters because if you make any path longer, it simply, the amount of stuff in the way is simply more, no matter whether you have a little bit of stuff in the way or just a lot of stuff in the way. If it's a longer path, it's going to be more. And it also depends on the area. If you have a really big area, it's like if you have a small hose, you can only get a small amount of current. But if you have a big hose and the water is moving at the same speed, you can actually have more current because more water can get out of that hose because it's got a bigger mouth to it. Yeah? Whoops, let's just go back a little bit. So you can see aluminum is more resistive than copper. So back in the 1980s, they built some houses with aluminum wiring. And if you ever bought one of those houses, you had to re-upgrade your wires because it turned out that those wires produce too much heat because that resistivity, the energy, instead of just flowing through, energy would be given off as heat, which could cause house fires, which is no good. And so why don't we use gold for our wires? Because gold has a much better conductivity. Too expensive. Copper is a good compromise. Yep. So the original one, it took about 6 seconds or so for all the marbles to flow through. Now we've got these obstructions, and the atomic structure of any sort of conductor will have some obstructions in it. It's just the electrons bump into things like some protons or whatnot, right? And so that's resistivity. And the more you make the resistivity, the slower the current. So you can see there's the same number of electrons there. Let's see how much time it takes for those same number of electrons to pass a point. Why did it only take 3 seconds? Same number of electrons. It's just wider. It's like, why would you rather travel on a 6-lane highway than a 3-lane highway if the amount of traffic is the same? Right? You'd rather travel on a 6-lane highway if the traffic is bad, right? Because you've got more places for the cars to drive. Okay, so a resistor could be anything. They have things that are specifically just resistors. They make the wire really, really narrow, and so it just slows down the flow of current because you don't always want current flowing very fast because it can cause heat to build up in the circuit and it can cause problems. Okay, but a lamp is also a circuit. Yeah, you think I don't know? Okay, Kimmy, you can come and sit beside Abby. And Jerry, you can come and sit beside Taiki. There we go. Okay, Jerry. Oh, no, you can't because I didn't see you. Gavin hid you. You can sit beside, Kimmy, you can sit beside Jazz. Okay. And Jerry, you can sit beside Taiki. You can sit right behind Ella, right here. Second row, right here. Okay. Yeah, for sure. There you go. Perfect. Excellent. Okay, so as I was saying, a resistor could be anything. It could be a specific resistor, but a lamp is also a resistor because it resists the flow of charge. If you remember, electrons bashing into things cause the atoms in the little filament of the bulb to jiggle faster, which made them heat up. And they heat up so high that they actually let off a glow because hot things glow. So lamps can be resistors, motors are resistors, resistors are resistors. Anything that slows the flow of charge is a resistor. And if you could put your phone in the cell hotel, please. Thank you. So it didn't matter whether we had that little red post causing resistance or whether we had a narrowing, okay, causing resistance. Both of them slowed the flow of electrons, okay? Okay, and that is resistance. And now we're going to fill in a few things here. So what is resistance? You should know this definition. Maybe a quiz on Thursday. Resistance is the opposition to the flow of current. It slows the current. It slows the flow. As current resistance gets higher, current gets slower. Which of those two variables would be your independent variable? The resistance or the current? Have a chat with your neighbor about it. Of these two variables, resistance and current, which is the independent and which is the dependent variable? Do you guys remember what an independent variable is? Which of those two is the one that you change? We change the resistance. Is the one we change the independent variable or the dependent variable? The one we change is the independent. Okay? Independent is the one we change. And which one did we change? We changed the resistance. Which variable responds to that change? The dependent variable responds to the change. And so that means our current is responding to our resistance. So the current is the dependent variable. If we were to graph this, where can I put a little graph? I could put a little graph over here. Which variable goes on the x-axis? The independent or the dependent? Independent. Okay, so on the x goes the independent. And so what would we label our x-axis in this case? Independent variable is resistance, so let's put resistance on our x-axis. Resistance. And that means that on our y-axis is the dependent variable. And that's going to be our current. Tell your partner what you think the shape of this graph will look like. As we increase the resistance, what happens to the current? As we increase resistance, what happens to the current? Does it get bigger or smaller? It gets smaller. And in fact, it gets smaller in this particular way. It does this. Okay? It starts high and it becomes lower, but it does it as a curve. Okay? It's a 1 over x function if you're into that sort of thing. But don't worry about that if you don't know what that is. You can learn that later in math. But if you've done the math, if you're ahead in your math, maybe that means something to you, maybe it doesn't. Okay? All right. So in the video, the marbles represented the electrons. So the marbles were the electrons. And the path represented the wire. Energy was provided by elevating one end of the table. So this is like a battery, okay? So the table was elevated like a battery is supplying a voltage. When energy is supplied to the electrons flow through the wire, and that flow of electrons is the electric current. Any resistance to the flow of the electrons will slow the current. So current, this little symbol here, may or may not be new to you. It means is proportional to. And if you want to draw that yourself, it is like an elongated fish. Okay? It's an elongated fish. And what is proportional to means as resistance increases, current changes as 1 over resistance. So as resistance gets bigger, current is going to get smaller. Because if you get a bigger number on the bottom, then this number becomes smaller. Does that make sense? Okay. This is what we call an inverse relationship. As one increases, the other decreases. Okay. Resistivity depends upon 3 things. First of all, resistivity. What is this weird little doodad? It's not the letter P. It is a Greek letter rho. And it's almost like a P, but it's sort of a bit more curvy than a P. Maybe a little bit like an upside down 6. Okay? If you draw it as a P, though, I won't get upset because it kind of looks like a P. But it's not a P, it's a rho, which means that it's an R sound when it's in Greek. We have the length of the wire, which you can either write as L, or you can write it as L. I don't like to write it like that because then it starts to look like either a 1 or an I, and that becomes confusing. Do you guys know what I mean when I say cross-sectional area? How many people feel like they know what cross-sectional area means? 1, 2, 3, 4. Okay. just in case you don't, what it means is if this is our wire, this right here, like if we cut it away, the area there, that is our cross-sectional area. When they say we cross-section something, that means we cut it in half and we look at the surface of what we have cut. And within that wire, if this is a wire, the resistance is going to depend on the length. It's going to depend on the cross-sectional area, A. And it's also going to depend on, you can imagine that we have little obstructions. That's not a big enough place to write the word obstruction. I need to pick a better place. I'm going to write it over here. Obstruction to the flow of current. Which is the resistivity. And the symbol for the resistivity is rho. Yeah, it's gone. My pen does crazy things. Let's make it look like a real O, shall we? Yes, thank you. So the resistivity is anything that's blocking the flow of electrons. The area is what we get when we cut it in half, and the length is obviously the length. So here is a question. Which of these three factors is being represented in this picture? Is it? Which one are we specifically looking at here? Have we changed the length? Have we changed the area, or have we changed the resistivity? We have changed the resistivity. By adding obstructions. What have we changed here? Have we changed the area? Have we changed the length, or have we changed the resistivity here? We have changed the cross-sectional area. Resistivity is a value which is specific to each Any guesses? Substance, yes. Okay, resistivity is specific to each substance. Certain materials have more obstructions, other materials have less obstructions. This is due to their natural structure. If the rectangles below represent the wire, which wire has a greater resistivity, A or B? Yes, B has a greater resistivity because it has more obstructions. Yeah. Because it has more obstructions. If electrons have to travel through the two copper wires in question 4, in which one, and you can see that they're pretty much like the same distance from each other, right? I guess I should maybe move those over so it looks more lined up. But in which wire will the electrons encounter the most obstructions, the most blockages to the flow of electrons? Wire A or wire B? B. Therefore, if a wire is longer, there are more obstructions in the path of the electrons, which will make the electrons flow slower. If you have a 1-lane road or 3-lane road, which road allows the faster flow of cars? 3-lane road. If you have a 3-millimeter wire or a 6-millimeter wire, which will allow a faster flow of electrons? 6-millimeter wire. Therefore, if a wire has a greater cross-sectional area, the current will flow faster. Excellent. You are not responsible for knowing this formula. Okay? However, if the numerator, which is the top, which is that part, increases, what will happen to resistance? It will increase. So resistance will increase. If the denominator, let's make that blue maybe, if the denominator, which is on the bottom, increases, then what will happen to resistance? It's going to decrease, because when you have a bigger number on the top, that makes it bigger. So if I said, we're going to start with 1/1, okay? If I make the top bigger, 2/1, the whole thing got bigger. If I make the bottom bigger, then that's smaller, okay? So when you increase resistivity, the resistance does what? If you increase resistivity, the resistance increases. What will happen to the current? It will decreases. If you increase the length of the wire, what happens to the resistance? The resistance increases, yeah, because you've got more obstructions. And what happens to the current? Current decreases. If you increase the area of the wire, what happens to the resistance? The resistance decreases and the current increases. So basically, anytime the resistance increases the current, tell your partner, every time the resistance increases, the current decreases. So if we wanted to have a formula that related resistance to current, would we say, there's going to be something else in here, but would we have that resistance is proportional to, no, you know what? I'm not going to do that yet. A direct relationship is when A increases, B also increases. An inverse relationship is when A increases, B decreases. What is the relationship between resistance and current? Is it direct or is it inverse? Yeah. Have a chat with your neighbor about that. Is the relationship between resistance and current, is it direct or is it inverse? If it's direct, an increase in one leads to an increase in the other. If it is inverse, then an increase in one leads to a decrease in the other. Talk with your neighbor about it. See what they think. What do you guys think? Inverse. Yeah, because as resistance increases, the current decreases, and that's what's happening in an inverse relationship. Yes. Is this going to be on the quiz? Not tomorrow's quiz. Okay, maybe on Thursday. Okay. So which would we say? Is current directly proportional to R, or is current inversely proportional to R resistance? And remember, you just answered this question. It's no different. Resistance and current have an inverse relationship. So current is inversely proportional to resistance. If you're planning on taking physics at all, this conceptual way of looking at things, just saying as this one goes up, this one goes down, what does this little proportional symbol mean? It becomes useful. If you don't get it this year, that's okay. It will help to have seen it before. Okay? So don't feel like, oh my gosh, I'm too stupid, I don't get this. That's because you're in grade 9 and this is the first exposure you've ever had to this particular language and this way of writing it. Okay? So just do your best, and this exposure will help you when you get to grade 11. You'll be like, oh, I've seen this before. Oh yeah, that made no sense in grade 9, but it makes sense now. Okay? So Current is inversely proportional to resistance. So which statement is true? Remember, this little symbol here means is proportional to. Is I proportional to R? Which means as R increases, I also increases. Or is I proportional to 1 over R, which means as R increases, I decreases. Oh my God, that was a long time ago. Oh! We were protesting. We were striking for better pay and better support for students. What? 2014 probably. Yeah. Super fun. Okay. Which one? Do they both increase the same, or does current go down as resistance increases? It is the second one. Okay. Which graph represents the relationship between current and resistance? Remember, you read the graph this way. As resistance increases, what is happening in this graph to the current? The current is decreasing. In this graph, as the resistance increases, what is happening to the current? The current is increasing. Which of those two is correct? The first one is correct. This one is wrong. Okay. So there are some questions here that you can try if you are interested in that sort of thing. If not, let's take a little watch of a video on Ohm's law. Okay? Yes. Do you guys need a little 5-minute break? Yeah. Okay, why don't you take a 5-minute break? Anyone want to go outside? We should all go outside. Everybody come outside. We'll go take a walk around the parking lot, and then we'll come back. It's beautiful outside. Let's go, everyone outside. We're gonna walk around the parking lot, or jog, or walk. Let's go, everybody. Let's go. We're just going for a walk. You don't even have to walk all the way. Excellent.
So the ceiling tiles have been replaced then. Because same place where mine were, like so the two right there were done. Yeah. They said you had ceiling tiles, like there's kind of tile open. Oh, what happened?
Oh, they went like I was going to the bathroom, but they're outside in the parking lot right now.
You know what? You know what they're doing?
They're just walking around.
Oh, they'll take a walk.
Yeah.
Okay. Well, thank you. Like only God would call it like. No, they didn't use like more than 1 hour at the same time.
Okay, we're gonna watch this quick little video and then we'll be done for the day. And because you guys have listened to a very, very heavy lesson all day today, there will be no homework tonight. Okay, you can practice for the quiz if you want to, but no actual homework, all right? Yes, let me go grab that right now.
Oh, thank you.
Okay, now we are going to focus on the I equals V over R when we do Ohm's law. That's our third equation, and that is the I am very right equation. Okay, so that'll be the third equation that we actually learn and use. So if you give a thing more voltage, the current will flow faster. If you give it more resistance, the current will flow more slowly. Okay, and that is where this comes from. So you would take your I equals V over R equation, which is the one we are going to use, because the current depends on the voltage and it depends on the resistance, and you would solve for R, right? So you would bring the R up, Ri equals V, and then you want R by itself, so you bring the V down. So now you have R equals V over I, which is the version that he's using here. And then, of course, you substitute and you solve. Yay! Look at that. And the only thing about this is that the symbol ohm is a little bit hard to draw. So you might just practice drawing two lines like that and attaching them with like a little semicircle. Okay, that's kind of an ohm. When I try and do them without doing it like that, they end up looking like this, which is, I don't know, but you know. And if we had more time this year, we would actually like go through and like learn all the color bands, but we're going to run out of time before that. So, but I think on Wednesday, I'm going to haul out some circuit stuff for you to take a look at and see what you can do with different resistors and measuring the current. So. Hooray. Does that make sense? You gave the electrons twice the amount of energy. Yeah, so they would flow at twice the speed. And if you change the resistance, to double, they would flow at half the speed. Uh-oh. Yep. What's up? Oh, what happened? Interesting. Huh. There we are. So we have a 9-volt battery. We have a 3-volt LED. What do you think the voltage drop across the resistor is going to be? 6 volts. Because anytime electrons make it from one terminal of the battery to the other terminal, they have to drop all of their voltage. And if they're dropping 3 volts in the LED, they have to be dropping the other 6 volts in the resistor. Ooh, do you guys remember that discussion we had about conventional current? Conventional current is the way that if you take electronics or if you study physics, they're probably going to teach you that current moves from the positive terminal to the negative terminal. And that's it for today. Have a wonderful evening, study a little bit for your quiz, and enjoy not having any homework. Thank you for your attention in a very long and maybe dry lesson.
So it's not finished, the homeworks.
Oh, excellent. Here's that page. There we are. Thank you, thank you, thank you very much, Arthur. Very good.
It might be one, but I don't know. I actually got 9 points.
You want it? I took a lot of it too.